Hello and welcome to this film, which is, as you can see, it's an introduction to the acids and bases topic. And in this film, we're really just going to discuss the meaning of some key terms, most of which we should already know from when we studied electrolytes. Okay, so hopefully by the end of this film, you will have reviewed the idea of what we mean by strong and weak electrolytes, and also we'll have had a look at a theory called the Arrhenius theory of acids and bases, which is quite simple, but also quite limited theory, which we'll see in later films has actually been replaced by a more modern theory. But it's important to understand that this is where things started, I suppose, with acids and bases. Okay, so first of all, electrolytes. Now, you should remember something about these, but just in case you don't, let's have a look at why electrolytes are called electrolytes. Okay, this particular diagram here has a sodium chloride crystal pictured. And sodium chloride we know is an electrolyte because when you put it into water, when you dissolve it, it will break up into ions, free moving ions, which can conduct electricity. Okay, they can't conduct in the solid state, but as soon as they are broken up by the solution, they can conduct. Okay, so any substance that will release ions into a solution when you dissolve it is called an electrolyte. Okay, you have to have these free moving ions if your solution is going to conduct, so your substance has to be able to produce ions. Now, that doesn't mean it has to be ionic, okay, but as it happens, all ionic solids are considered electrolytes, and so are all strong acids, even though they're not ionic. They're actually covalent, but when you put them into water, they break up into ions, okay? And in actual fact, we ought to be able to remember that all these substances are classed as being strong electrolytes. And knowing what that means is really, really important, not just when you're looking at electrolytes, but also when you're looking at acids and bases. Strong meaning that for every particle that you put into solution, 100% of them will split up into ions. Okay, so every particle you put in solution will break up into ions. Also covalent substances, but capable of producing ions when in solution, are the weak acids and bases, and they are unsurprisingly I suppose, termed weak electrolytes. Okay, so weak electrolytes, again, very important definition to know. A weak electrolyte is one which will only ionize partially in solution. Okay, so for every molecule I put into solution, only a small number of them are actually going to turn into ions. Okay, so make sure that you remember what sort of substances are electrolytes and which of them are strong and which of them are weak. We're going to deal in a minute with some specific examples that you need to be able to remember. Okay? First, we'll look at the difference between strength and concentration. So bearing in mind that strength, being strong or weak, is about whether you ionize completely or not. Okay? So if I took a concentrated solution of a weak acid, the one that we're typically expected to remember most is ethanoic acid. There are others. Okay, let's say I had quite a concentrated solution of it, say 10 moles per litre. Now you might be wondering, well, how concentrated do you have to be concentrated? Well, that's quite an arbitrary thing, and there's certainly no cut-off point. Okay, but if I took a dilute solution of ethanoic acid, or a more dilute solution, it would have a lower concentration than this one, but it would still be just as weak. Okay, because ethanoic acid is weak. Okay, so the strong weak thing is a black or white statement. It's are you strong or are you weak? It's not how strong or weak are you. Whereas with concentration, it's more of a shades of grey thing. So I could have a dilute solution. Well, maybe this isn't as dilute as I can get, certainly. Okay, 1 mole per litre. In fact, it's relatively concentrated for a solution of an acid, but it's a lot more dilute than this one here. Okay, of a strong acid, maybe, I don't know, HCl, hydrochloric acid. So this solution is more dilute than that one. It's also more concentrated than one that has a lower concentration than that. Okay, that might sound like an obvious thing, but the point I'm trying to make here is that whether you're concentrated or dilute is not a clearly defined thing. Okay, it's a comparative thing. Whereas HCl is strong because every HCl molecule that I put into water will break up into ions, whereas only a small number of ethanoic acid molecules will do that, which is why it's called weak. Okay, we don't get into, in the waste course, we don't get into how weak acids are, okay, or how strong they are. We just say that things are either strong or they're weak. Okay, so this is black and white. It's do you ionize completely or not? Whereas with concentration, you can be fairly concentrated but still be more dilute than something with a higher concentration than you. Okay, sorry if that sounds more complicated than it needs to be, but it's actually quite a simple thing. Okay, looking now at this Arrhenius theory of acids and bases, and just hurrying along a little bit because this film's starting to get quite long. How do we define an acid and a base? Well, according to Arrhenius, who was an awfully long time ago, he said that acids were solutions that had H plus ions in them. And quite often you see H plus AQ written as H3O plus AQ. It's important to realize those two things mean exactly the same thing, even though they look different. Okay? So according to Arrhenius, an acid is a solution with those ions in. And according to him, a base, well, that is a solution with OH minus ions in it. Okay? So it's quite a simple definition. Acids have H plus, bases have OH minus. But the limitation of this is that he only deals with solutions, okay? So if any acid-base reaction happens that isn't in solution, then you can't use Arrhenius's definitions because they're to do with solutions. Okay, and we'll see quite soon that there's another theory called the Bronsted-Lowry theory, which expands on this a little bit. Okay, now just very quickly, let's have a look at those specific strong, weak acids and bases that you ought to be able to remember. Okay, so the strong acids, first of all, here they are: HCl, H2SO4, and HNO3. You should know them by name and by formula. So hydrochloric acid, sulfuric acid, and nitric acid. Make sure you remember those three. Okay, there may be other strong acids that come up on tests and exams, but they'll have to be introduced as strong acids to you. Okay, you won't be expected to remember them. Okay, and moving on to strong bases, this is perhaps even simpler because really you're just talking about metal hydroxides. Okay, so anytime you see something with OH in it, like sodium hydroxide, that's going to be a strong base, or lime water, calcium hydroxide. Okay, so these are bases that ionize completely, just like the strong acids were acids that ionize 100% when you put them in water. Let's look at the weak acids and bases. Well, for the time being, because this is just an introductory film, so we'll treat it as if you're just starting out in year 11. Good weak acid to remember is ethanoic acid. Remember it by formula and by name. And a good base to remember is this one here, which people often call ammonium, but it's not, it's ammonia. Okay, so NH3, ammonia, is the weak base that is good to remember. Ethanoic acid is a weak acid that is good to remember. By the end of year 12, there'll be others you need to remember, but we'll cover those in due course. And finally, polyprotic acid. So one last term that we're covering here in this film, polyprotic, meaning you've got more than one H plus ion to give away, and we'll look at some equations for this later. Okay, but an example of one of these is H2SO4. It's got two H pluses that it can split into solution. Okay, another one that looks like it's got more than one H plus is this one here, ethanoic acid. But these three hydrogens here, they're not actually acidic. It can't give those away. So it's only got one H plus ion, so it's not polyprotic. Okay, this acid here, phosphoric acid, is polyprotic. H3PO4, it can give all of those three hydrogens away. Okay, so good ones to remember would be phosphoric acid and sulfuric acid. And remember that ethanoic acid, although it looks like it's got lots of H's, is not polyprotic. Okay, so that's an introduction to the topic. As I say, there'll probably be lots of unanswered questions in this one, but hopefully they will be covered in the films to come. If there's anything that confuses you here, you want to ask about, please make time to come and do that as soon as you possibly can.